continuing on in the notes, we're going to look at some examples where we get some practice calculating p-values and also interpreting them. So in this example, we're going to consider a test of the null hypothesis that mu is less than or equal to 100 against the alternative hypothesis that mu is actually greater than 100. And we're going to assume that the population standard deviation is 5 units. So this is an example of a right-tailed test. All right, the direction of the inequality in the alternative tells us what kind of a test it is. We're going to base our inference on a random sample of size 25, all right, that's selected from the population, and we're going to calculate the sample mean x bar from that sample. And so with that, what we're supposed to do here is compute the p-value of the test and draw a conclusion based on a significance level of 5%, 0.05. And so we're supposed to do it in each of these situations. So, for example, if the sample mean turns out to be 98.5, what is the p-value and what is the conclusion that we would draw? If the sample mean is 101.5, again, what would be the p-value and what would be the conclusion? And then finally, if the sample mean is 102, what would be the p-value and what would be the conclusion that we would draw? Okay, so on this sheet I've written out again the hypotheses that we're testing. All right, so this is a right-tailed test. The null hypothesis says that mu is less than or equal to 100. The alternative says that mu is greater than 100. We're assuming that the population standard deviation is 5. We're basing our inference on a random sample of size 25. The formula for the test statistic, z-calc, is x bar minus the hypothesized value, which is 100, divided by the standard error of x bar, which is sigma over the square root of the sample size. Sigma is assumed to be 5. The sample size is 25, so the square root of that is 5. And so in the denominator here we have 5 over 5, which is 1. And so the formula for the test statistic just simplifies to, in this case, x bar minus 100. Now we're going to use this formula down here in the three questions. So if x bar is equal to 98.5, that would imply z-calc is 98.5 minus 100, which is negative 1.5. And so the p-value of the test, because this is a right-tailed test, the p-value is defined to be, for this test, the probability that z, the standard normal random variable, is greater than or equal to the computed value of the test statistic, which is negative 1.5. And remember, since this is a one-tailed test, and in particular a right-tailed test, we don't take the absolute value of z-calc. All right? Now we get this probability from either maybe you can get it with a calculator, perhaps your TI-84 or 36X Pro, but I'm going to be getting these values from the standard normal table that we have. All right, and if we look up negative 1.5 in the table, we get a right-tailed area, which is what we need because the inequality here is pointing to the right. We get a right-tailed area of 0.9332. So the p-value, if x bar is 98.5, the p-value for the test is 0.9332. Now, how do we interpret this? How do we use it? Remember that we reject the null hypothesis if and only if the p-value is less than or equal to the significance level. The significance level we're using in this test is 5%. And so since 0.9332 is not less than or equal to 0.05, we would fail to reject in this first case. Now let's look and see what would happen if x bar is actually equal to 101.5. In that case, z-calc is 1.5. The p-value for the test is therefore the probability that the standard normal random variable is greater than or equal to 1.5. And again, we can get that from the standard normal table that we've got. That's 0.0668. Now, since that is not less than or equal to 0.05, we would not reject the null hypothesis at the 0.05 level of significance. So again, we would fail to reject. But notice that for this value of x bar, the p-value is quite a bit smaller than it was when x bar was 98.5. So what we're seeing here is that increasing values of x bar are causing the p-value to drop. All right, we're getting more and more evidence. As x bar increases, you have more evidence up against the null hypothesis. Okay, finally, if x bar is equal to 102, then zcalc is 2 units, and the p-value is therefore the probability that the standard normal random variable is greater than or equal to 2, and that is equal to 0.0228. Now, again, if we're using a 0.05 level of significance, since 0.0228 is less than or equal to 0.05, in this case, we would reject the null hypothesis. So, going back through the 3 cases, in the first case, x bar being equal to 98.5, there is not enough evidence, there's insufficient evidence at the 0.05 level of significance to conclude that the alternative is true, because the p-value is not less than or equal to 0.05. In scenario 2, when x bar is equal to 101.5, again, because the p-value is not less than or equal to 0.05, there is insufficient evidence at the 0.05 level of significance to conclude that mu is greater than 100. But if we get a value of x bar equal to 102, then because the p-value, which is 0.0228, is less than or equal to 0.05, we would conclude, in this case, that there is sufficient evidence to at the 0.05 level of significance to conclude that the mean of the population is bigger than 100. All right, let's move on to the next example. It's a related example. So we're going to consider the same test, the null hypothesis being that mu is less than or equal to 100, the alternative being that mu is greater than 100, and again we're going to assume that sigma is 5. We're going to assume that we've got a random sample of size 25 selected from the population. And in this case, we're going to assume that the sample mean from the data is 102. And so we want to compute the p-value of the test and then draw a conclusion based on each of the significance levels given below. We're supposed to draw a conclusion if alpha is equal to 0.05, draw a conclusion if we're using a significance level of 0.01, draw a conclusion if we're using any significance level that's greater than or equal to 0.0228, and draw a conclusion for any value of alpha that is less than 0.0228. All right, so here's the solution. So remember that for this situation, and assuming if x bar was equal to 102, we calculated in the last example that the p-value is equal to 0.0228. So this was calculated in that previous example. And the decision rule that we're going to use, this is how you make decisions using p-values. All right, we reject the null hypothesis if the p-value is less than or equal to the significance level being used for the test. Now, if the significance level being used is 5%, 0.05, then as we saw in the previous example, because the p-value, which is 0.0228, is less than or equal to 0.05, it's less than or equal to alpha, then we would reject the null hypothesis because the rejection criteria is satisfied. On the other hand, if we were to use a significance level, an alpha value of 0.01, then since the p-value is not less than or equal to alpha in that case, we would fail to reject the null hypothesis. Now, if alpha is any number between 0 and 1 greater than or equal to 0.0228, then, and recognize that this right here is the p-value for the test. And if alpha is any value greater than or equal to 0.0228, then the p-value in that case would be less than or equal to alpha. And so for any value of alpha greater than or equal to 0.0228, which is the p-value, we would reject the null hypothesis. If alpha is any value that is strictly less than 0.0228, then we would fail to reject the null hypothesis because for that alpha, the p-value would not be less than or equal to that alpha. So the last two results in that example help show or help point out why, for a given sample, the p-value can also be described as the smallest significance level for which the null hypothesis would be rejected. All right, let me say that again. Let's go back to these two results here. Okay, that's what we're referring to. The last two results in this example help point out why, for a given sample, the p-value can also be described as the smallest significance level for which the null hypothesis would be rejected. And it's because of this that p-value is sometimes called the observed significance level, right? The observed significance level. Now, I will also say that in some, well, probably in many journal articles, you will probably see the p-value being called the significance level itself, and that's really not correct. The significance level, you'll remember, is alpha. The significance level is the value of alpha that we are using in performing the test. And remember that alpha, the significance level, represents the probability of committing a type 1 error. So the significance level is something very specific. The p-value is something else. Okay, it's something very specific, and it's different than the significance level. But some people, some authors will call the p-value the observed significance level, and that's okay because that is different than the significance level itself. So you may see that terminology. I just want you to be prepared for that and to understand what it is they're talking about. The observed significance level is just the p-value for the test. So that is all I'm going to say in this video. The next batch of material is a little bit more lengthy, and so to keep the length of the video at a reasonable length, I'm going to stop the video for now. So we'll pick this up on the next slide in the next video.